Back in the day when Newton actually came out with his book, the Principia Mathematica, he wrote Newton's second law that F equals ma. He actually wrote it a different way. And he wrote it with reference to momentum and a force changing a momentum. So we're going to see what equation he wrote today and how that equation relates to our F equals ma and this new term that we now have called impulse. So what we do here in order to derive this equation is that first and foremost, we have to remember our equation for acceleration. So acceleration is equal to a change in velocity over time. So we know that delta V, change in velocity, that's just final velocity minus initial velocity. So if we take this equation for acceleration and then we plug it into acceleration in Newton's second law, F equals ma, we end up getting F equals m times the quantity V final minus V initial divided by time. Now that mass right there, it's actually on the numerator, even though we wrote it kind of a weird way. So if we put it on the numerator, it looks like this. And then I'm going to distribute that mass to both the V final and the V initial. So multiply it by both V final and V initial. We end up getting mass times V final minus mass times V initial divided by time. Now, mass times velocity, this looks really familiar, right? We've been talking about momentum. Remember, momentum P is mass times velocity. So really what we're getting here is our momentum final minus momentum initial over time. And then we can rewrite that as delta P, our change in momentum over time. Now, what we're going to do now with this equation is we're going to multiply both sides by time in order to get rid of it on the denominator on that right-hand side. So multiplying both sides by time, we get force times time is equal to change in momentum. So this thing, force times time here, this is actually what our impulse is. And we denote this by a capital J. That's our variable for impulse. So impulse is just a force F on an object over a time period T. So we can see that the greater the force, the greater the impulse. The greater the time period in which the force is acting, the greater the impulse. The units for impulse are newtons times seconds. And we can see that since impulse is equal to change in momentum, that those units have to kind of match up to our momentum units also, which is kilograms times meters per second. And if you remember that a newton is mass times acceleration, which is kilograms times meters per second squared, they actually end up being the same unit. So our units work out here. So now what we can do is we can put our variable for impulse in J, and we get impulse is equal to change in momentum. So what this tells us is that impulses are what cause change in momentum of an object, and that change in momentum is equal to the magnitude and the direction, really, because they're both vectors. Well, it's the magnitude of that impulse on the object. So the greater the impulse, the greater the change in momentum. The less impulse we have, the less the change in momentum. Now, I don't really like writing the equation this way. I would rather write it like this because I kind of know my variables a little bit better here. And it kind of skips a step. So here, again, force times time, this is just our impulse, and then equals our change in momentum. Now, I wrote it like this because really, when we have a change in momentum, it's because we have a change in velocity. We're usually not changing mass here. So I put my delta in front of velocity, and then kind of expanding that because I know delta is final minus initial. I get impulse, force times time is equal to mass times the quantity, velocity final minus velocity initial. And so this is our derived equation for that term impulse.